I've got two things up on the board here, one of which you should already know, and another thing which may be some new information. The new information is this definition. It's the definition of the natural domain of a function of this form, where I've got an exponential expression, but I've got some function of x in the base position and some function of x in the exponent position. The simplest such function would be just y equals x to the x, okay? But I could have something like y equals sine x to the tan x, or something like that. So both the base and the exponent involve the variable x. Generally, when we have a function, the natural domain would be every number for which that function is defined. However, we make an exception here, and we say that the natural domain is the set of all things where it does have to be defined. And that's the only requirement we have for the function that's in the exponent position. So g of x has to be defined. X must be in the domain of g or we wouldn't have an exponent. But we require a little bit more of the function that's in the base. We don't just require that it be defined, we require that it be strictly positive. So for example, with this function, the natural domain is not the set of all numbers for which that expression is defined, it's the set of all positive numbers. Now, this would be defined if, for example, I had negative 1. I can take negative 1 to the negative 1. That's just the reciprocal of negative 1. That would be negative 1. But that's not what I get when I plug negative 1 into this function, because that is not part of the domain. The reason for that is that if we allowed negative numbers in the base, we start to get a mess, because we're not allowed to take even roots of negative numbers. So, while this makes perfect sense for negative 1, it wouldn't make sense if I had negative 1/2, because that would be the reciprocal of the square root, which I can't take, of negative 1. So if we allowed negative numbers in the base, we would have to remove any rational number with an even denominator from the exponent, and we would also have to remove irrational numbers from the exponent if they went along with a negative base. That's just a mess. So to keep things simple, we just say, hey, if there are variables in both the base and the exponent, by definition, the domain is everything where it's defined and the base is positive. So for a function like this, we would have to remove any odd multiple of pi over 2, because that would make tangent undefined. But then we'd also remove any angle that terminated in quadrants 3 or 4, where sine would be negative, and we'd remove multiples of pi, because that would make sine 0. Okay, excellent. So probably you haven't encountered that rule or that definition before, but that is a matter of definition, and we'll be using that shortly. It's not immediately clear why that's useful information. It will become so. Okay. Then I also remind you of the power rule of logs. This is something you should know. If I have the log base b, and almost always we're going to be using the log base e, which is the natural log. But if I have the log base b of a power, a to the c, this rule says I can bring that power down and make it a coefficient. And of course it works in the other direction. I could take a coefficient and bring it up and make it a power. Okay. I'm just going to remind you of why that works. Let's just suppose that a was b squared and c was 3. Okay. Now, with this, that would mean that the log base b of a would simply be 2. That's the exponent I need when b is my base to give me a. Okay. So if I'm looking at the log base b of a to the c, that would be the log base b of b squared cubed. We've got a power to a power. When we have a power to a power, I know that I would multiply the exponents. So this would be the log base b of b to the 6th, but that's just 6. And 6 happens to be 3 times 2. 3 is my c, and 2 is the log base b of a. Okay. So this is essentially writing in logarithmic notation the power rule for exponents, that when we take a power to a power, we multiply the exponents. Now, why is that useful? Well, that's going to help us in taking the derivative of a function like this. Let's suppose I wanted to take the derivative of x to the x. Okay. Now, we haven't learned how to do that yet. We've got two rules that seem vaguely relevant. I know that I've got the power rule. That tells me that the derivative of x to the n is n copies of x to the n minus 1. But that works when the power is constant. That doesn't apply here because that's not a constant. I've also got my exponential rule. I know that the derivative of b to the x is the natural log of the base times b to the x. This is the most general version. If my base is e, which is the base I use most often, the natural log of e just becomes 1, and we usually don't bother to write that. But this rule works when the base is constant. And I don't have that here either. Okay? So, I don't have a rule for when I'm working with an expression, a function like this, where there are variables in both places, both the base and the exponent position. So here's what I'm going to do instead. I'm going to start by writing this as an equation. Y, my function, is equal to x to the x. And then I'm going to do the same thing to both sides. If those two functions are equal, I can do the same thing to both sides. And what I'm going to do is take the natural log of both sides. This is why I needed this definition, because you may not go around just taking the natural log of anything you want to. You cannot take the natural log of 0, and you cannot take the natural log of something that is negative. So, if you have an expression with variables in it, you have to know it's positive before you can take the natural log. We do know it's positive by this definition, because if the domain is everything that makes the base positive, a positive number to any power is going to give me a positive result. So, I've taken the log of both sides. Now, it seems like I've made things more complicated, but now I can use this power rule of logs, so I can bring that exponent down. So the natural log of y is x times the natural log of x. Now, I know how to take the derivative of this, because this is just product rule. Now, I don't have anything up there in that exponent position. It's just a product of two functions. I'm going to have to use implicit differentiation, because I had to take the log of both sides, so I no longer just have y by itself. But that's okay. I'll use implicit differentiation. So we'll take the derivative with respect to x of the natural log of y, and we'll say that's the derivative with respect to x of x times the natural log of x. Now here, this is going to be implicit differentiation, basically using chain rule. The derivative of the log function is the reciprocal function. So I'm going to get 1 over y times y prime is the derivative of the inside part. Here, we'll use product rule. Derivative of x times the natural log of x plus x times the derivative of the natural log of x. So we have 1 over y prime equals the derivative of x is just 1 times the natural log function is the natural log of x plus x times the derivative of the natural log of x is 1 over x. And if I want to, I can go ahead and cancel that x over x. So I can say 1 over y prime equals the natural log of x plus 1. I don't want to lose the information that x can't be 0, but I can still see that x can't be 0 because I'm plugging it into the natural log function. Okay, so let me clear some space. We had y was x to the x, and what we have now is 1 over y prime is equal to the natural log of x plus 1. I'm going to solve for y prime, so I'm going to multiply over by y. So y prime is y times the quantity natural log of x plus 1. Do make sure that's in parentheses. Both terms get multiplied by y. Now, ordinarily, when we use implicit differentiation, it's okay to have x's and y's in our final answer. But here it's not, because we didn't start with an equation that implicitly defined y as a function of x. We started with an explicit formula for y. So I'm going to just replace that y with x to the x. So that is my derivative for x to the x. What we've just done is called logarithmic differentiation. It's a really nice technique that we're going to use basically whenever we have something like this, where we've got an exponential expression with variables in both the base and the exponent position. When we have something like that, basically we take the natural log of both sides of the equation y equals f of x. We then use the rules of logs to simplify this side and then use implicit differentiation. So use rules of logs and implicit differentiation. Very cool. We'll try another example in a minute.